This module is about spatial analysis, and it covers the following learning objectives, including what is spatial scope and spatial selection, and how we apply set algebra to spatial selection. Then we'll talk about spatial classification and dissolve operations, followed by proximity functions and buffering. Then we'll talk about overlaying and how it is applied to vector and raster data sets. And lastly, we'll talk about network analysis and geocoding. So first of all, what is spatial analysis? The spatial analysis is a set of operations that are applied to coordinates or attributes, and they are based on some spatial criteria. For example, identify areas with slope greater than 5%. So this would be a spatial operation that can be applied for spatial analysis. Similarly, list all the roads with lanes more than one, or find all the stream gauges that were installed before 1970. All of these are examples of spatial criteria that can be applied for spatial analysis. Now, we can have these kind of spatial operations that can be applied in a sequence. For example, if we have some input data, we apply a first operation, then we apply a second operation, and each step will have some output that goes as an input to the next operation until we reach the final output. Sometimes we apply different operations to the same output, same input, and get multiple outputs, or some operations also require multiple inputs to get a single output. In any case, all of these are based upon some operations that are performed on the coordinates or the attributes of the data based on some spatial criteria. One of the important things when we are applying spatial operations is the scope of operation. When we apply the operation, where does it apply? So there are three levels of scope. First one is called the local operation. This is only applied to the individual feature. Then the other one is the neighborhood operation, where the operation is applied to the adjacent features. And finally, global operation, where the application is done on all the features. So here's an example. Let's say if the question is, what is the population in the polygon Utah? So that would be an operation on this individual polygon. So it's a local operation. It has nothing to do with what's going on anywhere else with other features. Whereas if we were talking about how many states Utah neighbors, so in that case we need to know the neighboring features, and so this becomes a neighborhood operation. So the answer would be there are 6 neighboring states of Utah. And lastly, if the question was how does Utah's population rank in the following states, then that's a global operation. To know that what is the rank of Utah, we need to know population in all of these features. So this would become a spatial operation with global scope. So we have local scope, neighborhood scope, and global scope. The other important operation that we perform on a regular basis is the selection or spatial selection operation. And this basically identifies a subset of features that satisfy a given spatial criteria. And this spatial criteria can be based on the geometrical characteristics, for example, its coordinates, size, or shape. And it can also be based upon topological characteristics, for example, adjacency or containment. Let's look at some examples to help understand. So first we look at the geometrical selection, which is based on geometry. For example, suppose our spatial criteria is find all the states that are entirely north of Arkansas. So here is the state of Arkansas. All the selection is based upon its latitude value. So all the states that have latitude larger than Arkansas completely will be selected. So we can see that Nevada and California have parts of the states that are not entirely north of Arkansas, so they are not selected. Similarly, this state doesn't have all of its portion, all of its area entirely above Arkansas or north of Arkansas, so it's not selected. And all these states that are completely north of Arkansas have been selected. So this is based on location. Similarly, in geometry, we can base it on size. For example, select all the states that have area larger than 84,000 square kilometers. So in this case, only the states that satisfy that criteria will be selected. We could have a combination of the two criteria in the selection process as well, using an AND operation, and we'll talk about this. But we can combine multiple criteria into using logical operations. Similarly, if we look at the topological basis for spatial selection, we can have adjacency. Find all the states that are adjacent to Arkansas. So that would result in these following states as the output of the selection process. But care has to be exercised here. The selection process for adjacency can be based upon only the common line or shared line between the two features, or it can be based upon the shared node. For example, the following states have shared lines with Arizona, but Colorado doesn't have any shared line but only a shared node. So if we applied adjacency based upon shared lines, Colorado will not be selected. Whereas if we apply the adjacency criteria based upon shared nodes, then Colorado will also be selected. Finally, the topological selection criteria can be a containment. Find all the states that contain Mississippi River. So Mississippi River is a polyline type feature, but the output of this selection will be all the states that have part of the Mississippi River basin. And that way we can apply a spatial selection criteria based upon topology. The other thing that we can do with the spatial selection is set algebra. So if our features are considered as a set with some values, then we can apply algebra to them. Algebra primarily means addition, multiplication, less than, greater than, equal to, not equal to. So suppose the set S is the set of the areas of all the states, so it will have 48 values for the continental US. Now, if we apply a condition that what are the states larger than 84,000 square kilometer in area, then this criteria will create a subset. So a subset A is all small s's that are coming from our main set S, and they satisfy this criteria that S has to be greater than 84,000 square kilometers. So you can think of spatial selection on these numerical values as set algebra. And here are some other examples. So find all the counties where state is not equal to Vermont, or state is equal to Vermont, or state is not equal to New York, or the area is greater than or equal to 1,000 square miles, or the population density is less than 250 persons per square mile. So you can see all of these criteria are spatial criteria, and they end up resulting in a spatial selection, which is a subset of all the sets of features. The other thing we can do is Boolean algebra in spatial selection. We have discussed Boolean algebra in the attribute table in applying restrict operation. But here we can apply the same concept. Suppose A, B, C are the three spatial regions, and if you are interested in finding A or B, then it will be the union of A and B spatial feature. It will be it will be everything that is in set A as well as in set B. And if we are applying A and B, then it has to be present in both. So it will be the intersection of the two sets. Likewise, you should look at the NOT and these composite applications of NOT or and logical operations. And here are some examples that how you would see it if you were applying it to spatial selection or even within an attribute table. Here's an example of Boolean algebra in spatial selection. Suppose we are interested in the polygons where the county is Rice, so Rice County. If you look at this shape, this is Rice County, and we also want the watershed to be canyon. So all of this orange area is the canyon watershed. And if both of these are applied, then it will be the intersection of these two features, and that would be this brown area. So hopefully this help you understand how we can apply Boolean algebra in the spatial selection process. So this is basically an intersection, and is same as intersection, or it would be same as union, and not will be same as complementary or complement.